Schrodinger's equation failed completely when someone tried to apply it to helium. Failed completely. However, it was subsequently modified in such a way that it works for all the atoms in the periodic table. So that's the difference between Schrodinger's quantum mechanics and Bohr's theory. Bohr's theory no one could figure out how to modify it. But the quantum mechanical theory, they did. And I want to talk to you about how that was done and the results of it. The distribution of the electrons in an atom that has more than one electron is called its electron configuration. And it is the most important factor in determining the properties of that atom. So our objective is going to be to try to figure out the electron configuration for not every atom in the periodic table. I'm not going to kid you. We'll not do a thing with the lanthanides or the actinides. Most of the other atoms we'll be able to deal with. So what are the characteristics of polyatomic atoms, poly-electron atoms from quantum mechanics? They're really pretty simple. The first thing is that the wave functions for the orbitals are the same as hydrogen. No difference. Okay? So all of the atomic orbitals, AOs, the AOs for the polyelectron atoms are hydrogen-like. And the only difference in there is in the magnitude of the quantum of the atomic number that's used. That has to be changed a little bit because the electrons interact with one another. That's where the change was done. The rest of it looks just the same. The same shells, the same subshells, the same orbitals, the same 2s and 3p and 4d. They're all the same. And we use the same set of quantum numbers to describe all those orbitals. So all that stuff you learned in Chapter 7, or at least I hope you will learn it pretty soon, applies to Chapter 8. So that's good. Are we off the hook? No. We're not, because we have to extend the quantum mechanical model to account for the interaction between electrons. And this was done in a very unexpected and simple way. The first thing that was recognized was that there is a principle that comes out of quantum mechanics that says if you look at a polyelectron atom, and it's got, let's say it's a boron atom, it's got 5 electrons. No 2 electrons in the atom can have the same set of 4 quantum numbers. 4? I thought it was 3. No, we have to introduce a new quantum number, the 4th quantum number, which is called the spin quantum number. And I'm going to show you, before you go home today, where this came from and the effect that it has. So the influence of the 4th quantum number is to limit the number of electrons allowed in one orbital to 2. So that will be coming up in just a minute. The next thing, and equally influential thing, is a more complex set of subshell energy levels. Instead of having all the subshells in a shell have the same energies, now all of the subshells in a shell have different energies. And there's a pattern to it, but it complicates life a little bit. So if we look at a plot of the energies of the subshells in a helium atom, okay, just in a helium atom, 2 electrons, polyelectron, wave mechanics shows that in a helium atom, the 1s is still the ground state like it was before. But the 2s and the 2p have different energies, and the s is lower energy than the p. The 2s is lower than the 2p. And for every shell, then the subshells will have an energy difference where S is below P, is below D, is below F. So it's always S, P, D, F for each shell. And that's simple and straightforward and easy to deal with until we get to the place where those energy levels of the old hydrogen shells get close together. Then when they subshell energies split up, they begin to overlap. And this is where it is no longer intuitive, and we need help from the periodic table. Well, I'm going to show you how to use the periodic table to get that help. First of all, I want to talk a little bit about where that fourth quantum number came from. An experiment was done, and I don't know whether it was first done with hydrogen atoms or something else. It might have been silver atoms. I can't remember my history there. But it works the same for hydrogen atoms. If you have a source of hydrogen atoms, not molecules, atoms, in a big vacuum chamber, and these atoms come out a hole and go through what's called a columnator here, where a beam is made, a beam of hydrogen atoms. This whole thing is in a vacuum chamber, a large vacuum chamber. And the path of the beam is directed between the poles of a strong magnet. Something very interesting happens. The hydrogen atoms split up into two equal groups. One of them is bent towards the south pole of the magnet, and the other is bent towards the north pole of the magnet. And this was taken to indicate that there's something different about hydrogen atoms, and what was different here was the spin of the electron when the electron's treated like a particle. The spin was quantized into clockwise, clockwise, and anti-clockwise. Clockwise and anti-clockwise. And because that's a spinning charged particle, it generates a magnetic field. And it generates a magnetic field that either has a north pole or a south pole. And depending on which pole it is, it's either attracted to the south pole or attracted to the north pole. Quantum mechanics designates this by using the quantum number m sub s, the fourth quantum number, the spin quantum number. It can only have two values, plus 1/2 and minus 1/2. So it's real easy to deal with the fourth quantum number. That's not a problem. So electrons in hydrogen atoms can have conceptually this spin. Now, I always had trouble as a student trying to think of this electron in a hydrogen atom as a wave and having a spin one way or another. And so what happened later on was that the Schrödinger equation was solved using Einstein's relativity model. And lo and behold, without having to assume spin, the electron's properties broke up into two groups of equal size, and the net result was you got the same effect as was seen experimentally here. So the fourth quantum number we can think of as describes electron spin, because I'm not able to teach you how Einstein's model of relativity did this. I can't follow it. I'm sorry. Too few brain cells left, I think. But here's what we'll do. If we can agree the spin quantum number m sub s represents electron spin, plus or minus, and this is plus 1/2 and minus 1/2 corresponds to spin in one direction or spin in the opposite direction. Okay, if you buy that, then Poly-exclusion principle is the last thing I want to try to cover today, and that is that no two electrons in that boron atom that I spoke about a minute ago can have the same set of 4 quantum numbers. What does that mean? Well, it's really pretty simple. The first 3 quantum numbers describe what part of an atom? N, L, M sub L, what is it? The orbital. They describe an orbital, right? And the 4th quantum number, M sub S, describes the state of the electron. So now, in looking at electrons in a polyatomic atom, we will put them into orbitals, and we will designate an arrow up for spin up or spin clockwise, and an arrow down for the opposite spin. So the electron in the ground state of the hydrogen atom might have n is equal to 1, L is equal to 0, and M sub L is equal to 0. Not might, it has to have that because that's the ground state. That represents this box. What is this box called? This box is called the 1s, atomic orbital. The electron in it, if M sub S is equal to plus 1/2, is recognized or is designated by an arrow with a spin going upwards. Now, that's the 1s. If we go to helium, it has 2 electrons. The Poly-exclusion principle said if those 2 electrons are in the same orbital, let's just suppose it's a ground state of the helium atom, and therefore the box for it is the 1s box, if you will. This is a box diagram. It's a 1s box, so that means it has n is equal to 1, L is equal to 0, and M sub L is equal to 0, defining that box. And the first electron to go in the box, according to something called the Aufbau principle, has the same 4 quantum number as the previous atom, which in this case was hydrogen. So n is equal to 1, L is equal to 0, M sub L is equal to 0, tells us the box is the 1s box. But M sub S is plus 1/2 because it needs to be just like hydrogen was. So the first electron in helium is identical to what we described for the electron in the previous atom, hydrogen. What about the second electron? The second helium electron occupies the same orbital. Right? That's the lowest energy orbital, so if we're talking about the ground state, it's got to be in the same orbital. So that electron is described by n is equal to 1, L is equal to 0, and M sub L is equal to 0. That's the 1s. That's the lowest available spot. But now, to keep the Poly-exclusion principle happy, its spin has to be opposite. So we put a negative 1/2 spin for it. And so that means 1 electron in helium is spin up, and 1's down. We call this spin paired. The spins are paired up in the 1s. And if you tried to put both electrons with the same spin, up or down, that would be a very unfavorable energetic situation. It would not be the ground state because it violates the Poly-exclusion principle, which is one of the main principles of quantum mechanics. So we conclude from this that atomic orbitals can have a maximum of 2 electrons because there's only 2 possible spins, and these electrons must have opposite spins. In lithium, for example, the first 2 electrons would have exactly the same configuration as the 2 electrons in the previous atom, which was helium. So we would have, in the first 2 electrons of lithium, a 1s with 2 electrons, and they would be paired. Their spins would be paired. The next electron is going to have to find another orbital because this one's full. We can't put any more in that, so we would go up the next step. The next available subshell would be the 2s. And the 2s, if we make a box for it here, we will put 1 electron in the 2s, and that electron will have spin up by convention. And its first 3 electrons are quantum numbers are n is equal to 2, L is equal to 0, and M sub L is equal to 0. That specifies the 2s. Okay? and m sub s equals plus 1/2 says the spin is up there. So we have now demonstrated what happens step by step as we're going upwards in the number of electrons and upwards in the energy of the available orbitals. Now I've changed this around a little bit. I put this workshop in here and I delayed the next slide. What are the values of the 4 quantum numbers of the 4th electron in beryllium? Well, if we look in the periodic table, beryllium has 4 electrons. It has 2 electrons in the 1s, and it will have 2 electrons in the 2s. And the question that we need to look at is, what about this 4th one here? This one here. What are the quantum numbers for the 4th electron? First of all, what's n? Say it. N is the shell, and it will have, this is the second shell, and so n will be 2 because it's the second shell. We filled up the first shell with the 1s. Okay? So n is equal to 2. What about L? What's L? Say it. 0. It's 0 because this is an S subshell. And we learned last time that for S orbitals and subshells, L is equal to 0. So we'll put a 0 in there. What about the m sub L value for this electron? Say it. 0. That's right. M sub L takes values from minus L to plus L.
How'd you get L equals 0?
I beg your pardon?
How'd you get L equals 0?
Because I gave you a list of subshell names or symbols, S, P, D, F, and so forth, and the one for S subshells was 0. And so m sub L has to be 0 because L is 0. Okay? What about m sub S? What's the value of m sub S? Write it down on your paper. Write the m sub S value down. Let's see will you get it right. If you don't have any idea what I'm talking about, listen. Everybody got it written down? What are the allowed values of m sub S? 1/2 or negative 1/2. In this case, it has to be spin down because the first electron was spin up. This has to be spin down. That corresponds to negative 1/2. How many wrote negative 1/2 down on their paper? Okay. If you didn't, do you understand why it has to be negative 1/2, or do you have any questions on it? Okay. So to do electron configurations, we have to watch out for the conventions. I've given you one of those. We have to count the electrons, and we have to know something about the order of subshells. Subshells in energy. Okay? So let's ask a question. Why is the lithium 2s lower in energy than the lithium 2p? They're both in the n is equal to 2 shell, but I put those electrons in the 2s. I didn't put them in the 2p. And why is that? Well, one of the things we said about multi-electron configurations is that the subshell energies that were always the same in a given shell for hydrogen were different. And what we have here is a result that the 2s is lower than the 2p, and the 3s is lower than the 3p, and the 4s is lower than the 4p, but why? Well, we have to look at several different effects that can influence the energy states. After all, that's what we're talking about, the 2p energy state and the 2s energy state. Most of these things have something to do with Coulomb's law. Here's Coulomb's law over here. The potential energy of the system is equal to a constant times the product of the charges divided by the distance between the charges. So if we have a potential energy diagram, and we have a positive charge like the charge on the hydrogen atom's nucleus, and a negative charge like the charge on the hydrogen atom's electron, if these two things are far apart, then that means that D12 is large, and that will make the energy of the system smaller. Now, it's going to be negative, so it's a less negative number. If we bring the two things together, the denominator gets smaller, so E gets more negative, larger, more negative. So we have to consider, when we're trying to compare energies, where the electron is with respect to the positive charges. How far is it from the nucleus? Because we said last time that the size of orbitals varied, and as n increased, we had the situation where the size of the orbitals increased, which boils down really to meaning the most probable or average place to find the electron is progressively further from the nucleus. Well, that has a bearing on this, as you can see right here. The nuclear charge is pretty straightforward. That's the Q1. Okay? That's Q1 over here. And if D is the same, then the energy will be influenced directly instead of inversely by the distance. It'll be influenced directly by Q1. So if we look at the hydrogen atom, where the charge in the nucleus is a single positive charge, and compare that to helium plus, where there's only one electron, but there are two protons in the nucleus, we now see we've doubled Q1, and these electrons are both in 1s. We're going to just make the assumption that D doesn't change very much here. And you can see what happens. Here, take a look at this, minus 1,300 kilojoules per mole compared to minus 5,000. That's a factor of 4. Double the charge in the nucleus, you're going to see a bigger effect, a large effect on the energy. Okay. This electron then is easier to remove because it's at less negative energy. This one down here is harder to remove. This orbital is less stable. This orbital is more stable. Everybody see the relationship all right? You have questions about it? Yes, go ahead.
Is energy the energy it takes to remove that electron?
He's asking whether the E in what we're talking about is the energy that would be needed to rip that electron out of there. And I can answer partially yes, that it's the negative of that energy. Okay? If you take the absolute value of E, that's how much it would take to remove that electron. So you're pretty close to the answer there. So nuclear charge is pretty straightforward. There's a couple of less straightforward things here. Let's see what the number of electrons has to do with it. Right? We know electrons are negatively charged particles. So if you bring two of them together, Coulomb's law is going to operate in the repulsive mode. And that's going to destabilize things. So let's start with our helium plus that we had on the previous slide. Two positive charges with one electron in the 1s. Let's add one electron to this system. As we saw before, that electron will go into the 1s with paired spins. So now we have two electrons here, and I put them out here kind of in an orbit because that's the way your book did it. But you have to realize that this is not a Bohr orbit. This is just representing the average distance, or the most probable distance of finding the electron. So what's going on now? The number of negative charges have doubled. However, there is now a repulsive interaction between the electrons. And if the electrons are anyways close to one another, that's going to be reducing the stability of the whole thing, making it less negative, if you will. And you can see the numbers here. In He plus with 1 electron, it's minus 5,000. With He with 2 electrons and the same 2 plus, it's minus 2,300. Okay, so again, 1 electron makes the other electron easier to remove. So whichever one of these is removed, it's going to be easier than this one. This one's harder to remove. Okay? Then this orbital is therefore less stable, and this one is more stable. Okay, so that's the effect of adding an additional electron. Questions on that?
The D in the first, in the top one, when you have 2 electrons.
Uh-huh.
What is the distance here? I mean, it's not by half because you add another electron.
It's a little bit more complicated than we talk about here because there is a D difference. D is smaller here because of the ratio of the charge than it is up here. So D plays a role, but I was scared to mention that because I can't tell you what role exactly that it plays. But it's not as big as the charge anyhow. You can see that with these numbers. Okay, next one. The effect of inner electrons on the energy of an outer electron. This is under the general heading of shielding. So if we go back to lithium 2+, I guess we didn't go lithium 2+. So if we go to lithium 2+, there's 3 positive charges in the nucleus, and there's only 1 electron left. The 2+ got rid of 2 out of the 3 electrons, so there's 1 electron. And let's just assume that that electron is in the 2s, even though that's not the ground state. Quantum mechanics will let us calculate the energy of that system, and it's just a little, it's close to 3,000 kilojoules per mole. Okay? If now we put electrons in this 1s, in this system there's no electrons there, and this outer electron is completely unshielded. It feels the full effect of this nucleus. But if we put some electrons in here, then there's going to be what we call shielding. And the shielding in the aggregate involves all of these terms that you see here. It's getting pretty complicated, isn't it? The 3 electrons will be attracted, each one of them, to the nucleus, and the difference will be in the distance between them. The ones in the 1s are closer to the nucleus, and the one in the 2s is further away. But then there will be 3 different repulsive effects, too. Electron-electron repulsion makes the overall effect on the 2s electron smaller than it is down here. So this electron is easier to remove because the other 2 electrons repel it. And this one down here, there aren't any other electrons to repel it, so this one's harder to remove, and therefore this orbital is less stable, and this orbital is more stable, more negative, if you will. Are we doing okay? Everybody see what's going on here? This is the third effect, the inner electron. There's only one more. Questions here? Okay. The penetration effect has to do with something we looked at back in Chapter 7, which we called radial distribution probability, or radial probability distribution. It was when we had our electron density meter and we started marching from the nucleus outwards, and we were recording the values of electron density as we got further and further out the R vector. Okay? Now, let's start here with a lithium atom. And in this lithium atom, we are going to make believe that there's only 1 electron, and it's in the 2p. Keep in mind that normally, in the ground state of lithium, this outer electron would be in the 2s. That would be the most stable place to put it. But we're going to put it out further. We're going to put it in the 2p. Put it out here. That's an excited state. And the question we have is, if if the 2p were actually lower in energy than the 2s, then that electron would go into the 2p first. But it doesn't. We saw that already. So let's look at what would happen if we put some electrons, if we put this electron in the 2s instead of the 2p, and we look at the radial distribution functions. Okay? This is a representation of the radial distribution function for the lithium atom. And this big blue area in here is the pair of electrons in the 1s. Those guys right there. Okay, they're in there close to the nucleus. Then here are the distribution functions for the 2p in orange and the 2s in blue. If you put the electron in the 2s, notice that there is a little lobe inside the 2p in the 2s, closer to the nucleus. If we put electrons in there, it's said to represent the penetration of the 2s in the electron density of the 1s. Now, the 2p doesn't penetrate as much because it doesn't have a little lobe like this. Okay? Now, it may not be evident from the diagram, but the penetration is greater for the 2s, putting the electron in the 2s, than it is the 2p, and therefore, if we look at the lithium with an electron in the outer electron in the 2s, this electron is going to be harder to remove because it spends a little bit of time in there very close to the nucleus. And the proportion that it spends in there is going to stabilize it more than the 2p is here. So this is called the penetration effect. And that makes the 2s more stable. That's the 2s. And it makes the 2p a little less stable. So there's the answer to the question where we started out. Questions about it? Okay? So the combination of shielding and penetration and the other Coulombic effects breaks the subshells apart in the way that's shown here. The 1s is by itself because it's the only subshell in the n is equal to 1 shell. But the 2s and the 2p are arranged so that, like in lithium, the 2s is lower energy than the 2p. So when you're doing the electron configuration, after you've filled the 1s, you fill the 2s next. Once the 2s is filled, then it goes to the 2p. The same thing will be true for the 3s, the 3p, and the 3d. Okay? So for a given n value, which is a given shell, the lower the L value, the lower the sublevel energy, more negative. So 3s is below 3p, is below 3d, 3s, 3p, 3d. And 4s is below 4p, is below 4d, is below 4f. Okay? But notice the top of the n is equal to 3 shell overlaps the bottom of the n is equal to 4 shell. They begin to overlap right in there. And that region will be a region where we'll have to pay special attention to figure out what the electron configuration will be. And we'll do that.